quantum biology, as we already mentioned, is going to be very unfamiliar to our listeners. It wasn't something that I'd thought much about at all before this. So I thought it would be a good idea to talk about a few examples. And the first that comes to my mind is it's actually what you begin life on the edge with is my namesake, the robin. And
Mm.
from the outside, these birds, I mean, certainly seem to inhabit the classical world that we do. But where do quantum processes come into shape their observable behavior?
This has become sort of the poster child of quantum biology,
It's a good
just
place to
because
start then.
it's so fascinating. Yeah.
Hmm.
um, so the European robin, which essentially lives its spring and summer up in northern Europe, Scandinavia, Sweden, Russia, and every fall it will migrate down to the Mediterranean looking for warmer weather, as many animals, marine mammals, birds, insects do. In a similar way that, for example, monarch butterflies will migrate every year from northeast Canada, eastern Canada, down to Mexico. In the 1970s, it was established that the European robin, that was, I think, the first creature that was confirmed to have this ability, that it was able to utilize among the many tricks that migrating animals use to navigate. It was able to sense the Earth's magnetic field, the angle of inclination of the magnetic field. So if you think about the Earth as a giant dipole magnet, the magnetic fields emerge vertically from the north and south magnetic poles, and then around the equator they're parallel to the ground. And so the bird in flying is able to sense the orientation, inclination of the magnetic field. There's a famous ornithologist couple in Germany, the Wilczkos, who would capture these robins in mid-migration and put them inside these little sort of containers, sort of cone-shaped, that have blotting paper, ink at the bottom and blotting paper up the side. So when the bird is at the bottom, it gets ink on its feet. And as it tries to fly to escape from these containers, it tends to want to fly out in the direction to continue its migratory journey. And so this is how they established that it was actually wanting to fly in that direction. How do they know it's a magnetic effect? Well, they put Helmholtz coils, giant sort of magnetic coils, on either side of the trap containing these birds, and they could have these coils in the reverse polarity to the Earth's magnetic field, with the same field strength. So when you turn them on, they cancel out any magnetic field. And when they do that, these birds fly randomly in all directions. As soon as they turn off the magnetic fields, the birds sense again the Earth's magnetic field, and they want to fly in a particular direction. So there was a famous paper in the 1970s in the journal Science that established that these birds, and later other marine mammals and insects, have a built-in compass, some chemical compass somewhere in the body that gives them directional information. Of course, the mystery was, where is this compass? How does it work? Now, here we are, 2023, and the only theory in town, the only theory that has survived, that is still in play, is the idea that quantum entanglement is playing a crucial role. So quantum entanglement, the idea that two separated particles are part of a single system. However far apart they are, you have to describe them as a single quantum state, which means that affecting one of them will influence the other. It was also established that this chemical compass, however it worked, resided in the bird's retina because it was light activated. And so,
Right.
there's a researcher in Germany, in Ulm, who designs these experiments where he covers these birds with, a bit like the executioner's mask that sort of covers the eyes.
Uh,
And once these birds can't see, they also can't sense the Earth's magnetic field. So it's triggered by photons entering the bird's eye. None of that is controversial. That is all sort of pretty well established science. Of course, what's controversial is, how does it work? The theory is in quantum biology that photons enter the eye. A photon will knock one of a pair of coupled electrons in an atom within a protein molecule called cryptochrome that sits in the back of the retina. The photon knocks one of these electrons off, so it sort of gets knocked off and it sits on an adjacent atom, still within this large protein made of, thousands and thousands of atoms. But these two electrons remain quantum entangled, which means that the way they spin, whether they're both spinning up or one spinning up, one spinning down, the way they spin is very sensitive. The way they dance together is very sensitive to their orientation in the Earth's magnetic field. So even though it's very, very weak, it has the ability, to influence this delicate, entangled state of these two electrons. And then when they collapse, when entanglement disappears, that sends certain messages to the bird's brain, telling it the orientation in the field. What's fun about this is that quantum entanglement famously was a phenomenon, a mechanism in quantum mechanics that Albert Einstein hated.
Right.
He called it spooky action at a distance.
Mm-hmm.
We are beginning to appreciate that quantum entanglement, and as part of my research at the moment, is a fundamental feature of reality. Fundamental that I feel we should be teaching undergraduate physics students about quantum entanglement. It's not really something they encounter in standard undergraduate textbooks yet. But the fact that quantum entanglement, Einstein's spooky action, helps the European robin navigate its way down to warmer climates every fall has a certain romance to it. I would like this to be the correct theory. Of course, liking something, wanting it to be the correct theory doesn't mean it's the correct theory. Mm-hmm. But it's a fun, interesting application of one of the weirder features of the quantum world, quantum entanglement, playing an important role in a living animal, helping it find its way.
Mm-hmm. Just a completely tangential comment. We can imagine what sight or smell are like for birds, but I wonder what it must be like to sense magnetic fields. And especially,
there's a paper that suggests that what the bird sees is like some sort of dark patch imposed, augmented reality on its field of vision, and it tries to centralize that like a pilot trying to get the crosshairs in there when they're flying in a plane.
I guess since you described this theory or this process visually, I mean, it's taking place in the retina, it would make sense that maybe they would experience it phenomenologically as visual phenomenon. But this also just came to my mind, but would you anticipate that, and maybe this experiment has been done, that if you moved these birds to the southern hemisphere, they would just instinctively start migrating in the exact opposite direction? Or is it sensitive to the polarity in it?
No, I think that's right. I mean, I'm not sure if anyone's done the experiment, but there may be other animals that have this magnetoreception, this sensing the Earth's magnetic field. But that would certainly be the implication. Wherever they are, if they're near the North Pole or the South Pole, their directional information will be towards the equator, towards the direction where the magnetic field is more parallel to the ground. So they don't care which hemisphere they're in. It should be the same thing, moving towards the equator.
And you also said that, I think this is just the only theory that's in town at this point, and it seems like it's very well formulated, but am I to take it that it hasn't been experimentally confirmed, and then would that be because of the reasons we sort of discussed earlier, where it's very difficult to do these experiments in vivo?
Yeah, absolutely. I mean, all you can do is experiment in vitro on individual protein molecules, the cryptochrome molecules.
Yeah.